Section: Introduction. In this section, we discuss the significant advancements made in developing large language models, LLMs, using Internet text datasets over recent years. These models have shown remarkable abilities across a wide range of tasks, leading some to believe that the future of artificial intelligence might simply involve making these systems bigger. However, we argue that this approach has its limitations. For one, the amount of publicly available text data that can be used for training is finite and could soon become a limiting factor. More critically, relying solely on natural language might not be sufficient to fully understand or replicate all aspects of intelligent behavior or to capture the complexities of the physical world. For example, explaining how to tie a knot using only words can be quite challenging. Despite these limitations, the Internet is a treasure trove of video content, with platforms like YouTube offering over 10,000 years' worth of video. This represents a vast source of information about the world, yet the potential of video data in training machine learning models has not been fully explored, especially when compared to text data. While LLMs have made strides in complex reasoning and decision-making tasks, video generation models have largely been confined to creating content for entertainment. We believe that it's time to rethink the role of video generation models. By drawing parallels with the success of language models, we propose that video generation could play a crucial role in understanding and interacting with the physical world. This involves recognizing that videos can serve as a comprehensive representation of the physical world, that a wide range of tasks can be approached through video generation, and that pre-training on Internet-scale video data can significantly enhance the capabilities of vision models, enabling them to simulate interactions, make decisions, and even take actions in the real world. To support our argument, we delve into recent research that utilizes video generation in various applications, such as solving tasks, answering questions, and simulating environments for robotics, self-driving cars, and scientific research. These applications leverage techniques like instruction tuning, in-context learning, and reinforcement learning, showcasing the potential of video generation beyond mere content creation. Finally, we acknowledge the challenges facing video generation, from technical hurdles to ethical considerations, and suggest possible solutions. Our goal is to highlight the untapped potential of video generation in making significant contributions to real-world applications, drawing a future where video generation models could become as influential and versatile as language models are today. In the preliminary section, we provide a brief overview of how video generation models work and their application in specific domains through conditional generation. A video clip is considered as a sequence of image frames, and conditional video generation involves modeling the probability of a video given a certain condition. This can be done using various models that either predict each frame sequentially or generate all frames together in an iterative manner. We also discuss how conditional video generation can be tailored for specific tasks based on the conditioning variable. This includes generating videos from text descriptions, creating video rollouts based on an initial image and a text description, and editing or stylizing videos guided by text. Additionally, we explore the use of video generation for learning visual dynamics, where the model predicts future frames based on current visuals and actions, offering a glimpse into the potential of video generation as a versatile tool for a wide range of applications. Section Summary. In this section, we highlight the limitations of relying solely on large language models, LLMs, for artificial intelligence tasks due to the scarcity of text data and the inability of language to fully capture physical world complexities. We propose that video generation models could serve as a counterpart to LLMs for understanding the physical world, enabling applications in robotics, self-driving, and science by leveraging the vast amount of video data available online. By drawing parallels between the capabilities of language models and the potential of video generation models, we aim to address challenges and unlock the full potential of video generation in real-world applications. Section: Unified Representation and Task Interface. In this section, we begin by explaining how videos serve as a comprehensive medium that can encapsulate a wide range of information from the Internet, thereby forming an extensive base of knowledge. Following this, we delve into how various tasks from the fields of computer vision and embodied AI can be approached as a conditional video generation challenge. This approach lays the groundwork for making decisions in the real world based on video generation capabilities. For those interested in the technical specifics of the models we use to generate our examples, we've included these details in the appendix, where you can also find additional videos we created. We argue that video stands as a unified form of representing information, surpassing internet text data in certain aspects. While text has been instrumental in the digital and intellectual realms, especially with the advent of large language models, it primarily excels at capturing high-level abstractions rather than the nuanced details of the physical world. Below, we outline several types of information that are challenging to convey through text but are effortlessly captured by video. 1. Visual and spatial information. This encompasses details like colors, shapes, textures, lighting effects, and spatial aspects such as the arrangement of objects in space, their relative positions, distances, orientations, and 3D information. Such details are inherently present in images and videos rather than in text. 2. Physics and dynamics. This includes how objects and environments physically interact, like collisions, manipulations, and movements governed by physical laws. Text might describe these interactions at a high level, but it often fails to capture the intricate details, such as the specific forces involved. 3. Behavior and action information. This pertains to human behaviors and actions, detailing the minutiae of task execution, like assembling furniture. Text can provide a broad overview of how a task is performed but lacks the ability to convey precise motions and movements. One might question the emphasis on video. We observe that video, much like text, is interpretable by humans, facilitating debugging, interaction, and safety considerations. Moreover, video is a versatile medium capable of representing information across various spatial and temporal resolutions, from the movement of atoms to the speed of light captured at incredibly high frame rates. Moving on to video generation as a unified task interface, we've seen from language modeling the importance of having a single objective through which diverse tasks can be expressed. This alignment between the representation of information and the task interface enables the transfer of broad knowledge to specific decisions. We demonstrate how a wide array of vision tasks, as well as more general question answering, reasoning, and problem-solving challenges, can all be framed as video generation tasks. In the realm of computer vision, tasks that were once considered distinct, such as semantic segmentation, depth estimation, and object tracking, can now be approached through a unified lens of video generation. This method involves structuring the input and output of a task within a unified image-video space, reordering image frames to present an input followed by its expected output, and leveraging in-context learning to guide the video generation model towards the desired task. Lastly, we explore the concept of using video as answers. In the evolving field of visual question answering, where responses have traditionally been in text, the advent of video generation offers a novel approach. For instance, in response to a query on how to make an origami airplane, a video could be generated detailing the process with high precision. This method of providing video responses to how-to questions could be more appealing to humans than textual explanations. However, it's worth noting that videos generated by current models tend to be brief and simplistic, often lacking the depth of information needed to fully address a user's query. This challenge of synthesizing video frames to answer questions shares similarities with planning and language models, with the key difference being that both the state and action spaces are now visual rather than textual. Section Summary. In this section, we discuss how video serves as a unified representation capturing diverse information types from the internet, enabling real-world decision-making through conditional video generation for tasks in computer vision and embodied AI. Video excels in capturing low-level details like visual, spatial, physics, dynamics, behavior, and actions that text struggles to express effectively. By converting various vision tasks into a video generation task, we create a unified task interface that allows for knowledge transfer and generalization across different vision tasks, similar to how language modeling unified tasks in natural language processing. Section: Visual Reasoning and Chain of Thought. In this section, we explore the concept of visual reasoning and the chain of thought process. We've discovered that by using a unified way to represent information and tasks, reasoning has become a significant part of language modeling. This means that a model can pull out relevant bits of information step by step to tackle more complex problems. Similarly, in the realm of video generation, we've started to see early signs of visual reasoning. This is evident when models predict what's missing in parts of an image. It's quite fascinating, and we're curious to see if predicting the next frame in a video could help solve more intricate geometry problems, especially if we add the right auxiliary lines through video generation. Building on this, we aim to delve deeper into how we can use next frame prediction in videos for visual reasoning and solving geometry problems. We've even looked into how videos can represent the execution state of algorithms, like the breadth first search, BFS, making learning to generate a video akin to learning how to search. While the examples we've provided might seem a bit far-fetched, they hint at the potential of using video generation as a way to train models to exhibit reasoning-like behaviors, similar to what we've seen in language models. This opens up new avenues for using video generation in tackling complex reasoning and algorithmic tasks. Moving on to the concept of video as a unified state action space, we've observed that video generation can encapsulate a wide range of knowledge and handle various vision tasks. We support this observation with concrete examples from embodied AI, where video serves as a unified representation and task interface. One major challenge in embodied AI has been the issue of data fragmentation, where data from one robot doing certain tasks isn't easily transferable to another robot or different tasks. This is mainly because each robot and task operates in its unique state action space. To overcome this, we advocate for using pixel space as a universal state action space across different tasks and environments. This approach allows embodied planning to be framed as a conditional video generation problem, benefiting from pre-trained video generation models on the internet. We can then add modules like inverse dynamics models or goal condition policies to translate high-level video plans into low-level robot controls. We've shown examples of video plans that look realistic and successfully complete tasks, highlighting the potential of using video as a unified state action space for embodied learning. Lastly, we touch upon the use of video generation as a form of simulation. This is particularly useful for optimizing control inputs in systems where it's challenging to explicitly model the underlying dynamics, like cloud movement or interactions with soft objects. We've studied visual generative simulators in gaming environments, where we can compare the quality of our simulators against actual game engines. This not only allows us to test the effectiveness of our simulators but also opens up possibilities for creating new gaming experiences that surpass current human-designed simulations. We've even trained a model that can simulate the dynamics of complex games, like Minecraft, by predicting future actions and observations based on past events. This model, which acts as both a world model and a policy, could significantly enhance model-based reinforcement learning algorithms by providing a more efficient way to sample from the dynamics model. In summary, our exploration into video generation for visual reasoning, embodied AI, and simulation presents promising avenues for advancing AI research and applications. Section Summary. In this section, we explore the potential of using video generation as a tool for simulating visual observations of various systems and processes, enabling optimization of control inputs based on simulation outcomes. By training generative models in game settings and real-world scenarios like robot interactions and autonomous driving, we can leverage video generation to create realistic simulations for complex tasks where explicit dynamics are challenging to express. This approach not only allows for testing the quality of generative simulators against ground truth simulations but also opens up possibilities for surpassing human-designed simulated environments in the future. Section: Generating Novel Game Environments. In this section, we delve into the fascinating realm of generating novel game environments. This area is buzzing with activity within the game AI community, as it holds promise for enhancing both the training and evaluation of reinforcement learning (RL) agents. There have been innovative attempts to use generative models for game design, such as predicting game frames or altering backgrounds to craft new game levels. However, these efforts have been somewhat limited by their reliance on specific simulation data and have only been conducted on a small scale. This limitation has curbed the potential for creating entirely new game environments. Recent advancements have shown that it's feasible to utilize unlabeled gameplay data from the internet to learn latent actions. This breakthrough allows us to train a video model that can be controlled through actions, opening the door to an infinite array of diverse and interactive environments, all starting from a single image prompt. We've seen examples where human players can control game trajectories by selecting latent actions from two unique starting frames. Although this exploration is still in its early stages, it's exciting to think about the possibility of integrating learned reward models to train RL agents in fully generative game environments. Moving on to robotics and self-driving, we tackle the challenge of simulating the SE3 action space. A significant hurdle in robot learning has been the difficulty of transferring policies trained in simulations to real-world execution. We've demonstrated that it's possible to learn a model that predicts the next frame based on actions, using real robot video data from the language table environment, which has a simple Cartesian action space. We've shown that this approach can predict the visual outcomes of more complex end effector actions in the SE3 space. An immediate application of a generative SE3 simulator is to evaluate robot policies, especially considering the safety implications of real-world robot testing. Beyond evaluation, we've successfully trained an RL policy using data generated by a simulator in the language table environment. An intriguing future direction is to combine simulated rollouts with real-world experiences, potentially using a Dyna-style algorithm to enhance learning. This approach would involve collecting real-world videos as the policy is executed, providing valuable feedback for the generative simulator. Moreover, generative simulators could revolutionize the training of multitask and multi-environment policies by allowing video rollouts in varied settings, a feat not previously possible. In the domain of robotics, navigation, and self-driving, another advantage of generative simulators is their ability to introduce natural randomness into the training environment. This randomness can significantly improve the real-world applicability of policies trained in simulations. Traditional methods achieve this through domain randomization, which involves manually setting rendering rules. This process can be tedious and often results in limited environmental variations and unrealistic effects. With generative simulators, we can introduce varied driving conditions, such as different weather scenarios or specific locations, enhancing the training of self-driving policies with a rich diversity of conditions and locations. In the fields of science and engineering, video serves as a versatile representation, impacting areas like medical imaging, image processing, and computational fluid dynamics. When visual information is readily available but the underlying dynamics are complex, video generation models conditioned on control inputs can serve as effective visual simulators. This approach can then inform the optimization of control inputs. For example, we've illustrated how a generative simulator can depict the movement of silicon atoms on a carbon layer when stimulated by an electron beam, using data from a scanning transmission electron microscope, STEM. Employing a realistic visual simulator in response to control inputs can address the challenge of limited access to specialized equipment in scientific research. However, further investigation is needed to ensure the validity and effectiveness of using visual generative simulators for control input optimization. Additionally, generative simulators offer the advantage of fixed computational overhead, which is particularly beneficial for processes like simulating electron showers, where traditional computational methods quickly become impractical due to the complexity of calculating pairwise interactions among a large number of electrons. Despite the promising potential of video generation, several challenges remain. In the following sections, we outline these challenges and propose potential solutions, aiming to advance the application of video generation across various domains. Section Summary. In this section, we explore the advancements in generating novel game environments and simulating SE3 action spaces for robotics and self-driving applications. By leveraging unlabeled internet-scale gameplay data, we can create diverse interactive game environments, while generative simulators enable the evaluation and training of robot policies in realistic settings, improving sim-to-real transfer. Additionally, generative simulators offer benefits in introducing natural randomness for training policies in diverse environments, impacting fields like medical imaging and computational fluid dynamics by providing effective visual simulators for complex systems. Section: Limited coverage. In this section, we discuss several challenges and considerations in the field of video modeling, starting with the issue of limited coverage. Unlike language data, which often finds its distribution within the vast expanse of internet text, video data suitable for specific tasks is not as readily available online. For instance, videos that are of interest for computational fluid dynamics, featuring long durations of fluid movements, are scarce due to their lack of appeal to the general public. Similarly, finding videos of specific robots performing certain tasks, like a Franca Amica Panda robot folding clothes, is quite rare. This scarcity underscores the need for a more concerted effort to gather and share domain-specific video data, exemplified by the creation of datasets such as the OpenX embodiment for robotics. Another significant hurdle is the limited availability of labeled videos. Taking the Mind Dojo dataset as an example, it boasts over 300,000 hours of Minecraft gameplay footage but lacks game action labels, complicating the training of models for policy or environment simulation. This issue extends to the realm of robotics, where many datasets feature robot trajectories without detailed annotations on the tasks being performed. To mitigate this, previous studies have employed image and video captioning models to generate textual labels, which can then aid in training text-to-image or video models. This approach, however, differs from video pre-training, which focuses on labeling videos with action data rather than textual information. Another strategy involves inferring latent actions or skills from video content, though the scalability of this method for capturing complex and diverse dynamics remains an open question. When it comes to model heterogeneity, the field of video generation has not yet settled on a definitive approach, in contrast to language models which predominantly utilize autoregressive architectures. We explore three types of models: diffusion models, autoregressive models, and masked models, each with its own set of advantages and challenges. Diffusion models, for example, excel in modeling continuous output spaces and allow for parallel sampling of multiple frames, but they suffer from slow sampling speeds and sensitivity to hyperparameters. Autoregressive models, on the other hand, are easier to train and integrate with multimodal generation but are computationally intensive and prone to drift over long sequences. Masked models attempt to combine the strengths of both, allowing for parallel sampling of image tokens, yet they introduce their own set of challenges, such as sampling bias. Looking ahead, future models may benefit from integrating the strengths of these various approaches and exploring latent spaces to reduce redundancy in video data. Addressing the challenges of generation speed and maintaining long-term consistency will be crucial for advancing video generation models. Lastly, we touch on the phenomenon of hallucination in video generation, where models may generate implausible dynamics or objects may appear and disappear unexpectedly. This issue can stem from various factors, including the prioritization of background over object loss or the inability of models to capture critical motion frames. Despite these challenges, we have observed attempts to generate realistic videos through the use of egocentric motions and user inputs, even when those inputs are unrealistic. Employing methods like reinforcement learning with external feedback could offer a pathway to reducing hallucinations in video generation models. Section Summary. In this section, we discuss the challenges of limited coverage in video data for downstream tasks, emphasizing the need for domain-specific video datasets like the OpenX embodiment dataset for robotics. We also address the issue of limited labels in video modeling, highlighting the importance of annotated videos for training policies and environment models, and the potential use of image-video captioning models to provide additional text labels for training. Additionally, we explore the model heterogeneity in video generation, comparing diffusion models, autoregressive models, and masked models, and suggesting potential solutions to combine the strengths of different approaches for better video generation models. Section: Limited Generalization. In this section, we delve into the challenge of limited generalization that arises when attempting to generate videos from any given image and text input. This task proves particularly difficult for content areas that the training data does not adequately represent. As we've discussed earlier, the issue of not having enough diverse data is quite prevalent, making this a significant hurdle. For instance, when we consider the diffusion model, a common practice is to initially train it on videos of lower resolution. We then apply a technique known as spatial super-resolution to enhance the video quality without causing the model to overfit, or in other words, to memorize the training data too closely. We propose that the root of the problem might lie in the high-resolution images and videos containing an excess of high-frequency information. This type of information is essentially details that are too fine or rapid for human eyes to discern. Our focus on processing and reproducing this kind of detail could be what's hindering the model's ability to generalize well across different domains.